Okay, please start.
Okay, today I will present the paper Adversarial Sample Detection for Deep Neural Networks through Model Mutation Testing. The author is Wang Jingyi and it is accepted last year by ICSE.
So this is, I think this is maybe the second paper of Jingyi. So Jingyi developed his academic careers, I think, based on this bunch of paper.
Oh, this is the second paper. Oh, okay.
I think that is supposed to be the second paper.
Yeah. Because in this paper, he cites his previous paper. Okay. And as usual, we start with the overview. It follows background, approach, evaluation, and discussion. So deep learning neural network is under threat of adversarial examples. One of the defensive mechanism is to make the model more robust by adversarial training. However, it increases the training cost. There's an alternative way. It's called adversarial detection. Suppose we have developed a face recognition tool, but we have limited budget and we cannot afford retraining. And we want to ask the question, is there a way to tell fraud faces from normal faces at runtime? The idea is that given an input example, we are going to decide whether it's an adversarial example or a clean example. If yes, then we alarm and report. So the focus is not to build a robust model, it's only for adversarial sample detection. The paper observes that for adversarial examples, they are near the decision boundary. Thus, if the decision boundary changes slightly, then the label of adversarial example are prone to change. But for normal examples that are far away from the boundary, the label won't change. For example, in this figure, the solid line is the original model. The triangle points are adversarial examples and the rest are normal examples. If we tweak the boundary, then the adversarial example cross the mutated boundary, but the normal ones are unaffected.
So everyone is welcome to raise questions. I think Ruofan have a very articulate explanation, so I think it's a good chance for us to ask her. Okay, please go on. Ruofan, so I have a question here. So given that there have assumption that the adversary samples are more likely located on the boundary, there's supposed to be an evaluation on that.
Yes,
right?
yes, I will discuss.
There will have an evaluation on this assumption. So, but of course, that's based on the adversary sample tag. Of course, I will have questions later. But in this case, if this assumption is really true, but I feel it's not necessarily true. But if really somehow true, we might base on these assumptions for our future adversary sample detection technique. Okay, please go on.
So the paper further defines 4 types of mutations they are going to use. Gaussian fusing, which replaces the weights with some randomly generated normal numbers. Weight shuffling, which is to shuffle the weights. And neural switching, just to switch the weights for 2 neurons. And the last one, neural activation inverse, which is actually times -1 to the weight. So it changes the activation status of a neuron.
It's more like that neuron send an inverse or inverse signal, right? From positive to negative and negative to positive. So as for these four neuron operators, how do they apply? They apply the NOR or they randomly apply selected mutation operators? Maybe you will need later, right?
I think I didn't include this part, but they need to select a rate to control how many neurons that are going to change. So they choose a parameter there.
So there are hyperparameters of how many
Yeah, it's a hyperparameter.
And the shuffle selected weight, that it means the randomly switch the selected
Neurons. Yeah.
first weights by the Gaussian distribution. So will you please be more specific about the Gaussian things?
So in each layer, they will first take all the weights and compute their mean and standard deviation. And then for selected neurons, they are going to generate random number following that mean and standard deviation and just replace the weight with this new random number.
So the Gaussian fuzzing is accounting for a layer instead of a neuron.
It is for neuron, but the mean and standard deviation are computed for each layer.
Yeah. Okay. But we need to randomly select a portion of neurons, right?
Yeah. So that portion is the parameter I discussed.
Yeah, I understand. So the mean and the deviations for each layer. So the idea is that we still do the perturbations, we still mutate the neural network model, but the results, despite the weights will be different, but the randomized or the mutated weights still conform to the original mean and the deviation.
Yes.
Okay, I see. No, please go on. Thank you.
So given this situation, we can actually identify adversarial samples by measuring their sensitivity with regard to mutated models. Suppose the original model is small f, then we have a set of mutated model generated from the original one. We denote it as capital F. The sensitivity, or so-called label change rate, is the percentage of models that have changed the label of X.
I certainly feel that this method could not be that costly as we discussed before. So anyway, so for Wikipedia, Zhang, you may listen this carefully. So for Wikipedia, the majority of the runtime cost lies on network connections, and the screenshot capture, right? So, but when those two steps finished, it only takes 0.2 seconds to make the prediction. And that's what we calculated before. But of course, if we turn into a different machine, and the performance varies. So if we just change the models, if we perturbate it for a few times, suppose we have 10 models. I'm not sure what is the basic F. So does their experiment indicate how large how many mutated models are there?
Yes. So they will keep generating the model until it is sufficient for them to make the decision. And actually, the number of models is quite large. It's on average 100 models. So the runtime cost is still not negligible.
Yeah. So in this case, that means it needs 20 seconds, right? So suppose it takes only 0.2 seconds to make a predictions. Based on their approach, we prepared 100 mutated models. I think 100 is not that enough, because 100, that means they just have another 99 copies of slightly changed model. So a more robust maybe go up to 1,000. That is still possible. Still more reliable. If it go to 1,000, that means we need 200 seconds for each one. So that definitely is not very. It is kind of expensive. Please go on.
So the larger epsilon x is, the more sensitive x is. But how large is large? So we need to define a threshold, epsilon h. If it exceeds epsilon h, then it's sensitive, otherwise it's not sensitive. But this simple threshold is a very coarse criteria to decide. It might happen that we exceed the threshold a little bit, but it's just out of luck. So the paper formalizes this threshold comparison by hypothesis testing.
No, sorry, I missed the threshold. This is threshold for
the label change rate.
Oh, the label change rate. It's called. How do you pronounce this the Greek character?
I think it's epsilon.
Epsilon. Oh, it's capitalized epsilon.
Eh? Oh.
Yeah, okay, that doesn't matter. Please go on.
So we let null hypothesis to be epsilon x is larger than epsilon h, and the alternative one, which is just the reverse, is epsilon x.
What does epsilon x? So you would like to, in this case, we would like to define.
We want to test this hypothesis.
And how to pick up? So which hypothesis means that we want to know how large is the threshold? Is a reasonable threshold?
No, epsilon h is peaked. Is peaked before we do the hypothesis, but epsilon x is involves some random variable, so we need to test it.
Involves some. So what does x means?
Epsilon x. Epsilon x is the label change rate.
The label change rate.
Yeah. The numerator is actually a random variable because we don't know how many of the models can change the label of x.
Let me think about it. So the random variable x, but we are working on a single model, right? We work on single model. Hello?
Yeah, but we want to test whether we are confident to say it exists the threshold or not. So that's why we established this hypothesis testing.
Let me think about it. So given a threshold, let me see the total number of mutated. So I see. So it's more like so it's not a model specific. It's more like a sample rendezvous. So suppose given maybe 1,000 adversary samples, or maybe even larger, we could see how many mutated models will be changed, will be sensitive, will be changed to this prediction.
Yes.
Okay. But as for the, okay, so each model will have a mutation rate, the label change rate, right?
A collection of model will have this label change rate.
Yeah, every model. I think every model will have. You can see we have, for example, we have n adversary samples, and we have n models. Let's say we have n models, and we have another n adversary samples. And each model will have a change rate here.
No, we compute the change rate based on the total set of mutated model.
Okay, so it's inverse for each adversary samples.
Yeah.
We're gonna see how many models has been changed.
Oh yeah.
Okay.
So X is only one sample.
Okay, so the random variable is not towards model, it's towards sample.
It's the number of mutated models that have changed the label of X. So the random variable is the count of model. Yeah.
Okay, so I got it. So does anyone have a problem here? Let me raise a question. So the most relevant students here, apart from you and I, are Zhang Chen. Zhang Chen.
Yeah.
You understand what we're discussing?
Yeah, kind of.
So let me raise the questions. Or Ruofan, will you please raise the questions for Zhang Chen to test how much he grasped your point.
So can I ask, what is the random variable in the label change rate?
Zhang Chen, have you learned statistics?
Yeah.
Okay, so you understand what is random variable?
Yeah, I need to recall a bit actually.
How about Zheng Feng? Zheng Feng, do you understand this question? Hello, Zheng Feng? Is Zheng Feng there? Oh, Zheng Feng is not here. How about Xiangling?
Yes.
Do you understand Ruofan's question?
I need to search what random variable mean.
Okay. So we're not in a position to answer this. Maybe Ruofan, you can briefly introduce what is random variable, so we can recap the student's memory. So we rephrase it again.
So random variable is some unknown variable that follows certain distribution, but we are also unsure what is the exact distribution of it. We only have a set of observed value, and based on the observed value, we may carry out some hypothesis testing to inference what is the distribution look like. Yeah, something like that.
Then
So
I guess,
you get the point, Xiangling?
Maybe so it's n, right?
Okay, so the random variable is using to describe, for example, if we toss the dice, suppose this dice is normal dice, so we have a random variable x to indicate the outcome of the dice. You get my point? Suppose there, I'm not sure I'm good at writing. So given a dice, this dice looks like cube, and this is 1, this is 2, and 1, 3, and there's another 4, 5, 6. The other 4, 5, 6, I cannot write it. I cannot draw it here. So when I randomly throw the dice, so there is outcome x, right? These x, the option x is 1, 2, and 4, 6, right? Right, 6. So not like these variables, and the outcome of the variables is unknown. We do not know. Suppose we have a try. We throw a dice. We never know what is the outcome. But anyway, we would like to have a variable to describe the expected outcome of this variable. So in this case, I think this is a part of the probability, the probability theory, right? That's a very, so this is from the distribution. This distribution is more like the uniform distribution. And how do I formalize the uniform distribution? So it's
yes, you 1, 6, 1,6.
1,6. So I should draw it here in this format, right? So that means if I for this random variable x, as long as we do throw a dice or so the outcome is a uniform distribution on 1, 2, 3, 4, 5, 6. So these are random variables. So this x is still a random variable, and this random variable is actually the outcome of the model change rate. So we have, in this case, we have 1,000 or 10,000 adversary samples, but whether these samples
wait, we have capital N of models, but we don't know how many of them can change the label of X. So
this is
model is random variable.
So
the model outcome.
This is still an event. This is still a random event. So in this case, we use the random variable to indicate. Suppose given adversary samples, and what ratio. So what's the rate of the model? How many model will be changed? How many models will have a different predictions given these examples? Okay, so I'm not sure I have made myself clear enough, but I think we need to go on. Zhengfeng is Zhengfeng there? Okay, Zhengfeng, I'm not sure. Zhengfeng, I think Zhengfeng is not here, so let's keep going on. Hey, how about Aaron? Aaron, is Aaron there?
Yeah.
Aaron, you understand this point?
A bit.
A bit, okay. So, but this point is not so relevant to your research, but it's good to recap some idea of the serial probability.
Yeah.
Okay.
Okay. So we further simplify the H0 and H1 to be H0 to be epsilon x is equal to a number that is larger than epsilon h, and H1 to be a number that is less than epsilon h by delta. And we let n to be the total number of mutated models, and z is the random variable I mentioned. It's the number of mutated models that change the label for x. Okay. If H0 is true, then the likelihood of observing capital Z H equal to small z is this quantity.
I feel kind of lost. I can't if you kind of lost. This is a binary. This is a binary distribution. This a
binomial distribution with parameters n and p0. So in total, we have n trials because we have n mutated models, and each model has a probability of p0 to be changed. Yeah. So
do you have the label changed? So can I go back to the previous slide? The previous slide. I mean previous slide. Yeah. So this hypothesis. So given
I think we do this simplification just for easy of just because the testing will be easy, because it is not easy to test inequalities, but we can test equality. Yeah.
So here, so how is it? What is the point of the delta? The delta. The H1, H0, and H1.
Oh, because we want to test some kind of equality instead of inequality. It is very hard to test a p that is larger than epsilon h, but we can specify p to be a specific number here. Okay, so that's why we can write the likelihood like this. Otherwise, the p0 and p1 cannot be a specific number.
Previous slide. I think I need to recap some of the statistical knowledge as me too. For me too. So epsilon x is random variables, and so this threshold is epsilon h is defined by is manually defined value.
Yeah.
So it's going to based on my human knowledges of probability theories. So this is the event, right? Basically, this is the event. We would like to suppose here we somehow need this let the event to be E. We somehow need to evaluate PE to be to larger than 0.95. Am I correct?
Yes.
And would you please specify more? And this is
a here I think they use a different technique other than the traditional kind of hypothesis testing. So here they are comparing the likelihood ratio between non-hypothesis and alternative hypothesis. So you can see in my last slide, in my next slide, they compare the ratio here. So if the ratio is small, then the likelihood of having P0 is larger than P1, then we accept it. So it's a different testing procedure.
Okay, so maybe I'm not that familiar with this procedure. We'll be back to the previous slide. So because you mentioned there's simplification, hypothesis simplification. So you transform the inequality to equality representation, right? So this data is random. Does this data random?
No. It's also our choice. Yeah.
It's also a choice. So you would like to the rate is equal to. But so there's so large number of choice, right? There's so large number of choice of data. Z is the number of mutation models. Okay, maybe I can leave this behind. I can raise questions when you introduce later. Okay.
Oh, okay. So if on the other hand, if each one is true, then we can write the likelihood like this. This will just replace P0 with P1.
Z is the event.
Z is the event. Z is the random variable. And Z is the number of mutated models that change the label of X. So we are calculating the likelihood of capital Z, which is equal to our observed value, small z.
P0. So P0 is the probability.
Okay.
I'm just checking the formula. Jiangling, so do you have any question for this slide?
Like, what's capital Z again?
Capital Z is the random variable.
Capital Z is the random variable, indicating the number model, the number model changed, giving an individual adversary samples.
Yes, and small z is what we observe. So given that we have observed capital Z is equal to Z, we want to calculate what is the likelihood that H0 is true, and also what is the likelihood that H1 is true. If this ratio is very extreme, then we are very confident to say that H0 or H1 is true. Okay.
Okay.
Okay, so when we try, we just try the frequency, right? We just count the frequency about.
Yeah, just count the frequency.
Okay, please go on.
So if this ratio is small, then we prefer to accept H0. Otherwise, if PR is large, then we tend to reject H0.
Please go on.
So this is the detailed algorithm. Firstly, we initialize n is equal to 0 and z is equal to 0. Means initially we don't have any model. And in every iteration, we are going to add one more mutated model to capital F. Then we compute the statistic PR. If it is less than or equal to beta over 1 minus alpha, then we just stop.
Please annotate where the where you have described it on the algorithm.
Then we just stop and accept H0 and conclude that X is adversarial. Otherwise, if PR is larger than 1 minus beta over alpha, then we reject H0 and conclude that X is normal. But if this PR is in between of these two thresholds, then this is inconclusive. So we need more evidence. So we are going to add one more model to our capital F.
I still need to recap a bit. Model. So when they selected a mutation operator, they selected in a random way?
Every time they stick with one mutation operator. Oh, this is the mutation I mentioned.
So that means they have prepared a large number of the.
No, every time they only generate one.
No, I'm asking. They have already prepared. They have already prepared a large number of adversary samples.
Yes.
And so they start with 0 mutated models.
Yeah.
I added a more mutated model, so more get. So suppose that means suppose given 1 mutated models, and this model is sensitive to all the adverse samples, then the algorithm stop.
Yeah, stop.
Why they design such algorithms? So why we do this in an incremental way? So why not we suppose we randomly pick up the specific mutation, and this mutation will cause a radical change for the original model. So in this case, this algorithm just stop for the single model.
I think it's to save the efforts, because when our existing mutated models are sufficient, and then we can make the conclusion and stop. So we can reduce the number of mutated models we need to generate. Yeah.
So what do you mean that this algorithm is generated on the runtime?
Yeah.
If it is generated on the runtime, so it must have upper bound, right? So it must have upper bound of the number of mutated model.
No, don't have.
I think this is for experiment. It's not for runtime. Or if I understand correctly, why this have to be a runtime model? So what this algorithm for? Do we apply these algorithms on the runtime model, or do we apply this algorithm for the experiment?
The paper didn't discuss what is the application scenario, but I infer from the paper that it can only be applied at runtime because it didn't retrain the model.
Yes, whatever, we do not need to retrain the model.
Yeah.
So I think for this stage, according to the logic of your presentation and this paper, we are still at the stage of verifying the hypothesis, right? So this is somehow verifying whether adversarial sample can be well perturbated to cross the boundary.
No. It is we designed this algorithm to classify the example to be adversarial or clean. So it's a classification algorithm.
It's already being the classification.
What do you mean?
So shouldn't we first evaluate the hypothesis? Hypothesis of the adversarial sample lies alongside the boundary.
Oh yes, I will discuss in the evaluation part.
So in this case, the approach has already taken the assumption, saying that as long as I mutated some part, if that is the case, these algorithms is just definitely will be provided on the runtime. But if it just provided on the runtime, so it's still possible. It's still possible the number of mutated models keep growing.
Yeah.
Keep growing, and so we still have a way to stop it, right? So how do we decide the algorithm stop? So how do we? The point is that how do we stop here?
It's only when we accept each null or reject each null. Otherwise, we need to continue.
So this algorithm is possible to not terminate it forever.
Yeah.
So does the paper discuss this point?
No.
That is weird. Keep growing. So we should start with so for intuitive, or at least for my intuition. So a more straightforward way is that we prepared 100 or maybe 1,000 mutated models, and how do we get it? I don't care. We just prepared maybe 1,000 models there. So when given a model, when given an adversary sample, or given what a sample, we do not know it is adversary or not. So we feed the model we feed the samples to those models. We feed the sample to those models and to see how many models have their prediction changed.
And then test the hypothesis.
Yeah, then they're using, for example, their threshold. So isn't that a more straightforward way? And for this algorithm, it seems more complicated, and some part of details is very hard to be justified.
Yeah, I think that is also possible.
Maybe I can raise this example to Jingyi directly. Okay, please go on.
Okay, so I did a math derivation here.
Oh, you did it yourself, or it's on the paper?
I did myself.
Okay, that's great.
So PR is the quantity, right? And because we know n is fixed, so we can separate this constant out and group all the terms that involve with Z together. So if PR is less than or equal to beta over 1 minus alpha, it can be shown that it is equivalent to say Z is less than or equal to this quantity. And similarly, if PR is larger than or equal to 1 minus beta over alpha, we can reduce it to be Z is larger than or equal to this quantity. So it's a relationship between Z and N. If we draw these two inequalities on the graph, it will look like this. So you can see these are the two lines. These are the two lines. And the x-axis here is the N, and y-axis here is Z. So the blue region is where we can reject each null, and the green region is where we can accept each null. The yellow band is where we make no decision. So the alpha beta here actually controls the weights of the acceptance rejection region. Yes.
Okay. So here's come back to the P1 and P0. P1 and P0 are constant, right? And P1 and P0 are constant, and alpha beta is still constant.
Constant. K is also constant.
Yeah, so in this case, it's just, I understand you transform the probability description into
a graphic.
In a more physical, have more meanings, and they did a really good job. So in this case, why not we just, so here the question is, why bother we introduce those kind of variables? We can still just use the ends to draw the boundaries here. So that will be in that before.
I think the alpha beta here controls the type 1 error and type 2 error.
So what is type 1, type 2 error?
Type 1 error is, Type 1 error is when we reject each null, but actually each null is true. Type 2 error is when we accept each null, but each one is true. So it's something to control the false positive and false negative. Yeah.
Interesting. I think I need to read the papers, and also I need to admittedly I need to improve upon my own knowledge of the statistics, and I will have your advice when you go through more details. Okay, please go on.
So, okay, let's go through the evaluation part. So let me answer your question. It first validates the assumption that whether there is a significant difference between the label change rate of adversarial and normal. So we look at these few columns, the normal example column, the normal samples column, and also the adversarial sample column. So these are basically just, they use different types of adversarial attacks, and they compute the label change rate. So we can say the label change rate is much higher on adversarial samples than normal ones.
My question is that, or the successful attack or the unsuccessful attack? So when they do the perturbation on do they only use perturbation, or do they only use adversary samples on successfully compromising model?
I'm not sure.
Not sure, right?
Mm.
So the number, so here is because you can see the number, the mean, the mean number actually differs a lot of different approaches. Especially what raised my interest or curiosity is black box. This black box, the black box, so giving this black box, that black box means that we do not apply in a gradient descendant approach, and we will have these samples just like Johnson did, just like Johnson did. So it's highly likely that the successful rate of the black box is lower than the other approach, right? I mean the attack success, the success ratio of attack. So I'm going to raise questions. That means that a large number of the black box will not cross the boundary. Am I right?
Yeah, because the black box attack is not generated based on the original model, so the adversarial sample shouldn't lie near the decision boundary, and the label change rate shouldn't be such high.
Right. So here is the data I'm doubted about it. I'm just somehow doubt about it. Yeah. And then so that's why I'm going to raise the question on whether they only kept the successful attack. That's the only explanation. So then I will going to raise another question, is that if they only focus on the successful attack, and why they supposed to have similar results, and why this number will be so low? Does the paper have any explanation for that?
No. I think maybe for this kind of adversarial attack, our assumption does not valid anymore.
CNW deep food. Yes. So one of the interesting questions here is that the black box one. So I guess they were using the samples to cross the boundary. They were the sample to cross the boundary, and they only kept those.
Oh yeah, they only kept those success attacks.
They mentioned it, right? They mentioned the word captured. Also, it does not make much difference for CIFA 10. You can see 0. The ratio is very slow. Definitely, there's a significant difference. We can easily set a threshold, but it becomes very hard for us to pick up a threshold. You get my point? Right. So this point is 0.12 to ratio of maybe. So even if increase, the ratio is very clear, and the ratio boundary here is not very clear. But anyway, they have a conclusion that the majority of the adversary samples lie. And also it depends on how they apply the algorithm. So when they apply the algorithms, whether the adversary sample algorithm stop immediately after they find an adversary sample. You get my point. That means here. So suppose this is cross boundary, and this is a normal sample, right? So the process of adversaries generation is more like this way, right? So suppose So the adversary test, suppose after they apply the adversary samples, and finally reach here, and as long as the prediction is inverted, or reverted or changed, they stop. So definitely it will be lie aside the boundary. It's highly possible that the attack will keep going on. Then it will be then it is still possible, right? It's still quite a but it will be removed across after cross boundaries still keep going. So in this case, even if the module perturbation a bit and the detection will fail.
Yeah, but in principle, the adversarial they will save efforts. So once they change the label, they will stop. But that is in theory.
Not necessary. So when this depends on how you define the fitness function when applying the adversary sample generation. Right, the fitness is that to minimize the fitness for one label or maximize the fitness for the other label.
Yes, and also you need to make the perturbation to be small, so that's why you cross boundary then just stop.
Yeah. So so actually, so when you're doing the perturbation, it will be always small. So given images, you do the adversary sample, but you just change a few pixels. So the change will always be small. So your latter constraints is very relaxed constraint. But let's focus on the previous fitness, our discussion of fitness. So when we apply the adversary sample attack, the fitness will be either to minimize the fitness to minimize the fitness with its original label, or maximize the fitness to the other incorrect label. So in this case, as long as of course when we given here, we can stop here, but it's still as long as we can keep optimizations, it can still keep going, right? So I'm just asking. So suppose they have adversary samples. Of course, it largely depends on the space. It largely depends on space. So I still have a gut feeling that the adversary samples are not necessary stay on the boundary. So it highly depends on the shape. If the landscape of such space have the gradients, so it will just keep going. So if you keep going, the assumption will not true, unless there have assumption that there is a huge local optimas between the boundaries and the other side. So it's more like, suppose, let me look into here. Suppose this is the boundaries, and it will do gradient descent here, right? Unless all the shape looks like this, then it will stop at. You get my point?
But it won't happen, right? If you move far away from the boundary, then the fitness will just increase. So there will not be a local optimum near the boundary.
Yeah, so I'm saying that unless there's a local optima, local here, unless the local optima here, and there's a hue here, otherwise the gradient descent is always going on. We'll always keep going. Unless so there's two possibilities. First, they run the algorithm stop immediately after the label cross the boundary. The second is that the landscape of search space have a local optima here, so it not keep going. Of course, it's also possible that the local optima is more like this, right? So it is more like, so it after it crosses it, and they keep crossing, they keep going. So the difficulty, there's a lot of challenges for him to keep going, right? But even if the landscape looks like this, it is still possible. It still largely depends on the technique to generate adversary samples. So suppose they have so they can try to randomly change the learning rate to have a leap from or have a jump from the original space. So they're still able to have a cross boundaries to suddenly drop the node here. It is still possible, right? So here I somehow have a questions and doubt on how they implement their algorithms. Maybe I can ask Jingyi or the other students or Sunjun directly for how they consider their this research work. Okay, Ruofan, please. Let me raise a question. Xiangling. Did you understand what we discussed before?
I
kind of lost.
Yeah, kind of lost. Yeah.
Okay, no problem. So the video is always recorded and put on the YouTube. So if you're interested, you can have a check. Okay, Ruofan, please go on.
And the second research question is that how good is the label change rate as an indicator to classify adversarial versus clean examples? Because it's a classification task, so we can compute the area and the ROC curve. They use two baselines here. The first baseline uses the combination of density estimate and model uncertainty estimate as a joint feature. So this is based on the intuition that the distribution of weight when fitting into adversarial or fitting into normal would be different. The second baseline they use is their previous paper. In their previous paper, they used the label change rate of imposing random perturbations on the input sample. So instead of using mutated models, they just perturb their input and compute the label change rate.
Oh, sorry, so the label change rate computer. So this is one to that means they using different threshold to calculate our RC curve, right? So the baseline is the density estimate. What is density and the model uncertainty estimate the joint feature? So
I think they take the last layer of their model, then fit it into adversarial, and also fit into normal example and observe the difference between the distribution of this weight in the last layer.
The second
should be different. Yeah.
The second is LCR of imposing random. Okay, I see. So the second one is easy to understand. So they will compare the random perturbation with the adversary sample, right? They compare to see the difference of LCR. And the first baseline is that they're going to, with the same adversary samples, compare the LCR. That the first baseline. I think these two baselines answer different questions, right?
Yeah, the first baseline didn't use LCR,
right.
but it can achieve the classification. So yeah, they just
so maybe you can explain more about what is density estimate and the model uncertainty estimation.
I didn't go into the details for this paper, but I think basically, if we are fitting into adversarial sample, then we expect the last layer, because usually the last layer is for the classification. We expect the last layer to be quite noisy.
The last layer quite noisy.
Right.
Yeah,
but for normal example, maybe only one of the.
Maybe later you can send this. So this is another adversary sample detection technique.
Yeah.
Yeah. So they're using two different features. So density estimation for the last layers, and the model intensity estimation is more for the other. Maybe we can look into this, but this also can be considered our baseline. Sorry, I still need to interrupt a little bit. Zhang Chen. Is Zhang Chen there? Hello, Zhang Chen. I think,
Hello. Yeah.
yeah. So I'm not sure you're still following, but I suggest that this work is quite relevant to FYP. So I expected you, even if you kind of lost, but I suggest still encourage you and then suggest you follow. Try your best to follow. So that when you go through the videos, when you read the papers, it will be easier for you. It will still save the time.
Okay.
Okay, thanks. Ruofan, please go on.
So they compare the area and the ROC curve for baseline and also for the 4 kind of mutators they are using. The highlighted numbers are the best approach for each adversarial attack method. We can see that using label change rate based on mutated models is not uniformly better than all the not uniformly better for all adversarial attacks. And the label change rate based on random perturbation, which is baseline 2 here, is actually good enough.
Baseline 2.
Yeah, baseline 2 is their previous work. And these 4 columns are the 4 kind of model mutators they are using. Yeah.
I feel a bit hard to read these.
So these are different kind of example generated from different attack methods. And these are the area under ROC curve. So we want to maximize this number, right? And the highlighted number are the best approach for this GSMA attack and for CW attack and so on and so forth.
So it seems that baseline 1 still achieve good detection accuracy on this one?
Yes.
And the baseline 2 achieve good accuracy on this one. And also it seems that it's somehow comparable, right?
So yeah.
So and why baseline 1 does not have the
I'm not sure about this.
Okay, please go on.
So the gain of having mutated model is not that significant, and also they use easy data set here, like the minis and Cypher 10.
Okay. And for the baseline 2, isn't baseline 2 just to compare LCR? As far as I understand, sorry.
The classification, AURC.
Yeah. So as your in your slides, I still think your slides are confusing on the previous slide. Will you please go back to the previous slide? Yeah. So you are saying using LCR.
Using LCR as an indicator for the classifier.
So it means that they train a classifier.
No, the hypothesis testing we discussed before is just a classifier, right? It's just to reject or not reject.
Yeah. We need as long as we set a threshold, we can reject and not reject.
Yeah. So that's basically a classifier, right?
Yes. And for this baseline, my question lies here. So given LCR imposing random perturbations, so I always think there's a difference. So still using the LCR because the way to calculate LCR is always the same, right? So I think for the second point or second bullet, you are going to compare the effects of applying LCR on the random perturbation and the adversary samples.
No, here I'm going to apply random perturbation on both adversarial sample and clean examples. and then observe the label change rate. And their label change rate should also differ. Okay.
Oh, yeah.
And the label change rate for adversarial sample should be higher when applying random perturbations.
The random perturbation
is on input sample. So, yeah.
So when we are calculating LCR, we are always using mutated model. Is my this sentence true or not?
Oh, I think for baseline 2 here, they are calculating LCR based on input samples instead of model.
So in this case, you should not use I'm not sure whether you are using the terms in the papers or the other.
Yeah, in the paper, yeah.
So this LCR is not this LCR. Am I correct? LCR causing the random perturbation. So giving each sample, we apply a lot of perturbations.
Yes, then we have a set of samples. Then we also count how many of them has changed the label. So the intuition is same as the mutated models one, but here we replace model with input sample.
And so in this case, is the multiple samples and one model structure, right?
With one model, yes.
One model structures and and how do they? Oh, the idea. So the idea is that. So basically, but that's based on how the. Oh, I got the point. I think it's the point. So this is the boundary, right?
Yeah.
Suppose this is adversarial samples. It can perturbate it will generate its neighbors along by its own. It's going to see how many of the labels cross the boundary.
Oh, yeah.
Right.
So for baseline 2, we actually perturb the input, but for this paper, they perturb the boundary.
Yeah. So I think that makes things clear.
Yeah.
Okay. So next slide.
So research question 3 is to.
I'm going to check the results. Still check the results here. So. And why those results is not available?
I'm not sure. You have asked this question?
Right. And also why these results is not available? Right. Given adversarial samples and all those, because I do not know the details of baseline 1, but for baseline 2, it's highly intuitive that for this suppose there's an argument for the adversarial sample generated by this attack, and giving as long as this DF method can generate adversarial samples, do the random perturbations and calculate the corresponding LCR. Right. And as expected, I think the result, because baseline and their existing approach taking the same rationale, so by right they should have the same effect. Right.
Same effect.
You should have the same effect. You have at least a similar effect. Okay, please go on.
And the next research question is to evaluate which mutator is more effective in detecting adversarial versus clean. Recall that we have in total 4 mutators. So they evaluate three things. The first one is the detection accuracy on adversarial examples, the detection accuracy on clean examples, and the average number of iterations needed in algorithm 1. So you say they need maybe 100 mutated models to decide. This is mean.
So comparable. Do you think they are comparable?
Comparable.
Of course.
Roughly the same.
The best one is Gaussian fuzzy. The best one is Gaussian fuzzy.
Gaussian fuzzy, yeah.
And the worst one is the neuron switch. But not necessary. So they have different pros and cons. The neuron switch may detect to have more accuracy for the clean one. So they should have an overall. They should have an overall accuracy, right? Instead of the separate them.
I think their previous paper, which is the AUROC, is somehow like overall. This is on Cypher 10. So the paper recommends to use Gaussian fuzzy and neural activation inverse.
Okay.
The last question is, what is the cost of our detection algorithm? Because we need to generate mutated models and perform forward propagation to obtain label. For a single sample, the total time would be n times CG plus CF. N is the number of mutated models. For m samples, the total time would be this. And there is no m in front of CG because each mutant can be used on all samples. So we can see CG is very large.
Yeah, it seems that overall it incurs a lot of runtime overhead.
Yeah. And also we need to time n to CG, so it's even larger.
So if it takes if it is so expensive, it's very hard to believe it is a runtime algorithm. It's very hard to believe.
Then I don't know when we can apply this detection if it is not.
So in these papers, I overall have two questions. The first question is, I still doubt this rationale. So despite that largely depends on how they generate the virtual samples. So if they just stop immediately after they found the virtual samples, there's no doubt all the generated versions are along the boundary. However, I'm not sure if we can have tried a bit. Maybe we can try a little bit because it is quite easier for us to check whether it's on the boundary. Of course, if we can combine with Xianglin's visualization tool.
So we need to visualize it.
So somehow visualization is one for us to really understand what things going on, especially for example active learnings, adversarial sample generations. We can always understand the process, the progress of generating adversarial sample and applying active learning. So in this case, so we can just have a check if this boundary, if this adversarial sample is on the boundaries, it somehow provide a confidence close to 0.5, right? Somehow close to 0.5.
If we have multi-class, then it will.
If you have multiple classifiers, that means it means that the first option and the second options have very similar score before the max, right? Somehow we can do this. We can have this check. So if possible, we can do the adversarial sample generation by our own. So we keep training the adversarial samples to see if it is really in the boundary. So you can see the adversarial samples and the boundary, because based on their ideas, so as long as it cross the boundary, so it means that let me take sigmoid as a simple examples. So 0.5 is actually our boundary. So if it crosses 0.5, if it crosses 0.5, it crosses a boundary, right? So after boundaries, we keep optimizing the adversary sample. So to see how much we can, let's see how far we can go. So if given adversary samples, it stops at 0.6, 0.55, so it means if most adversary samples can no longer be optimized around 0.6, suppose the original score is below 0.5, it can pass up to past 0.5, and it can but it can no longer be optimized over 0.6. It means that their assumption is true. Otherwise, if it can further optimize until prediction to 0.9, if a majority go there, that means our experiment is counter. So even in this case, we do not even need to ask questions. We can just do our own experiment to see. Maybe you can sample a few hundred samples and try to keep optimizing them to see whether these samples still linger alongside the boundary. If it is not, if our experiment result, my gut feeling is that those, if we keep optimizing the adversary samples, they will not linger around the boundary. If your experiment shows that my assumption or my gut feeling is true, so that means they have a fundamental flaw in this paper.
Then do you want Zhang Cheng to have a try? I think it's quite related.
Sure, definitely. I think Zhang Cheng can involve. So before Zhang Cheng fully understand your adversary training, Zhang Cheng can play with these ideas for them to build up Zhang Chen's expertise. Zhang Cheng, is Zhang Cheng there?
Yeah, I'm here.
Yeah, do you understand what we discussed?
Sorry?
Do you understand what we discussed just now?
I wasn't paying attention, sorry.
So the idea is that, so I will raise it here, but I think Ruofan will provide more explanations later. So what are we trying to analyze is the rationale. So the paper they published on 2 years ago and 1 year ago. So the basis, all those part of the approach have a basic assumption that the adversary samples is lying alongside the boundary, decision boundary. Jonathan, do you understand what is decision boundary?
Decision boundary, yeah.
Yeah. So they mean the idea that the majority of adversary samples is lie alongside the boundary. So suppose the original samples here, and the process of generating adversary samples is more like these pictures. You understand this one?
Sorry, the one below is for?
The one below is origin.
Origin, okay.
The one here is target. So the process of generating adversary sample or learn adversary sample is just moving the original sample across the boundary, right? So then we have assumption that they have assumption that the adversary sample, that means the point T, is very likely to lie alongside the boundary. So now what we're going to do is that we adopt a adversary generation approach to keep mutating. So we have a doubt or question is that after they cross the boundaries, they just stop. They will not keep optimizing the point T anymore. So if the point T can be further optimized, so it will be very likely that adversary samples will keep optimizing. The adversary sample can keep optimized and becomes far and far away from the boundary. So means suppose T reach T prime, and T prime that no longer lie alongside the boundary anymore. So what you're going to do in your task is to evaluate whether we can further optimize T to T prime.
Okay.
Yeah, so that's the basic idea. So you can select a few thousand of samples. You can select a few thousand of samples. You can do the experiment to see whether you can push T to T prime. As long as the idea is how to push T to T prime is that T is T, the confidence or the confidence score of T in the original model, in older model, is more like about 0.5. That's why we believe it is like alongside the boundary. Hello? Right? So once we do this, as long as T prime is either close to 1 or 0, so that means it has already been away if the confidence value of T prime is either close to 0 or 1, maybe above 0.7 or below 0.3, so that means this T prime has been away from the boundary.
I see.
So we let Zhang Cheng to try on minis and Cypher10
Yeah, just based on their data set.
and use the existing adversarial attack method.
Yeah, you can just pick one of them. That's fine.
Then which adversarial should I pick?
Sorry?
Which adversarial method should I use?
Arbitrary. I think FGSM. Right?
FGSM, okay.
I can just use FGSM to do this.
Okay.
FGSM is quite simple, right? It's just a single step. So we don't expect it to go far away beyond the boundary. I think maybe choose the rest. Yeah.
Choose the okay. Okay, the rest I don't really know. So
Sorry. So why we don't choose FGSM?
Because FGSM is just one step attack, right? So we don't expect it to be move further after T. It's not an iterative one.
FGSM is not iterative.
Yeah, it's one step.
One step zero? Okay, so you can just choose multiple iterations. Okay. So the point is that whether we can find a set of or a large number of adversarial samples which counter their rationale. Okay. 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 I think we can. That's all for Ruofan's presentation.
No.
Okay.
So I have a discussion here. So as for their approach, from statistical point of view, I think the PR ratio test requires independence, which makes the mutated model have to be independent. But in fact, they're not, because they all come from the same original model. And second thing is, it is tricky to select the threshold epsilon h. It may be different for different data sets. There's no golden rule to decide how sensitive is sensitive if we don't know what kind of adversarial examples will come. And also for the research question one, so it's not easy to defend against black box attack because they do not necessarily lie near the boundary. For research question 4 is that the detection time will be huge because the time grows linearly with the number of inputs. And it takes around 100 iterations to decide a single example. Okay, that's all. Thank you.
Okay, so it's the view of the threat validity of their approach. Okay, I think Ruofan have made a fairly clear presentations, and we have thorough discussions in depth. And Zhang Chen, now you have a job to deeply understand evaluating the state of the art work. So I think you can take notes and update them in the Google Docs.
Okay.
Okay. Next one is Aaron's. Is Aaron there?
Yeah.
Okay, please go on. Now it's your turn.
So can you just screen?
Yes, again.
Yes, again. Yeah. Okay, so yeah, this paper is about a bug-driven hybrid testing called Savior.
So where is it published?
Sorry?
Where is this paper published?
I'm not very sure.
Okay, so the next slide. So in the follow-up paper presentations, we always require that you need to also present the venues published. This paper published. Yeah, I think this should be published on a security venue.
Okay. Yep. So so there's been like two main methods of finding software vulnerabilities. So one method is called fuzz testing, or like fuzzer. So basically what it does is just randomize inputs and try to detect, try to have a higher code coverage from there. And this is good because it tests programs quickly, but it's unable to explore more complex conditions where the inputs that it requires are very specific. And so one way to solve this problem of complex conditions is using concolic execution of testing. So this concolic testing basically uses symbolic execution and tries to find the path condition to reach those hard to reach code. So yeah, it can solve the complex path conditions. This method is quite slow. Yeah, so these are two ways to find software vulnerabilities, or actually just to generate tests through code coverage. So one common way to solve the limitation of both of them is to make them together and make it a hybrid testing. So we use the fast testing for path exploration, and then when we meet complex conditions, we switch to concolic execution, and in order to like reach those hard to reach code. And yeah, so basically this guides the fuzzer to new regions for code exploration. So this hybrid testing method is basically good for code coverage. However, it can be inefficient in detecting vulnerabilities. So the first reason why this is inefficient is because it's inefficient in actually reaching the vulnerable code. So this is just a brief description. So like all seeds that you generate from the fast testing are valued equally. So some of the seeds actually are not very useful because they do not reach.
I'm not sure what is my point, my problem. So I feel that your sound is not that continuous.
Oh, my microphone, you mean?
Yes, I feel that the sound is not so continuous. Is that so that you can closer to your microphones, or not sure whether there's problem in your network?
Yeah, it could be my Wi-Fi.
Okay, so if it's Wi-Fi, we can do nothing about it. Let's keep going on.
Yeah. Yeah. So I'll just repeat myself. So the first reason it is inefficient is because like all the seeds that you generate from fast testing are valued equally. However, some of the seeds can be more important than others because some of the seeds might actually reach code that are vulnerable. So if you waste time on seeds that are not vulnerable, then you might eventually time out before you actually cover the vulnerable code. So this is one example. The left side is the target program, and seed 1 is the first seed that is generated by fast testing. So the gray code blocks are the code blocks that the fuzzer managed to reach. However, at line 20, which is this if packet type equals to cat 1.
And so where the buggy code?
The buggy code is here at the red one, the pcap handler 2.
Okay, so that means in line 10, we need to make the branch equals not true. Or make equals to true, or make equals true,
Yeah.
right? So, but in this case, how do we now, but the problem is that how do we now package handler 2 is buggy?
Yeah, so as in now this example is showing why because if we don't order the seats, right, then we will actually visit this 22 first before this 11. But
I
actually,
understand, but my question is that how do we know the pcap handler 1 does not have a bug and your point is that pcap means that pcap handler 1 has already been visited and this does not trigger any bug.
Okay, so the thing is, we assume that we know that pcap handler 2 has a lot of bugs.
Okay, so
for
this is based on domain knowledge.
Yes.
Okay.
Yeah.
So in this case, we just need to measure how close the test is to those manually labeled code branch. Is that all? So that means we manually selected a few branches which are supposed to be more buggy, and we pay attention to those branches.
No. So the thing is, what we are doing is we are just trying to cover all the code, and at the same time we are trying to find bugs from them. Yeah. So as in this example is saying like, so assume that we don't know where the bugs are. Okay. So the fuzzer will generate this seed 1, and then because it gets stuck in line 20, so it can never reach it doesn't reach line 22. Okay, so it gets stuck at line 20, so it mutates to seed 2, and seed 2 has this path execution instead, and then it gets stuck again. And then this time we based on how your hybrid testing works, maybe like it times out at this seed 2, and then we switch to concurrent execution. So now concurrent execution, because seed 1 was generated first, okay, so it solves the line 20.
Sorry, let me rephrase. C2 is derived from C1, or C2 is involved from C1, right?
It's mutated, yeah.
It's mutated from C1, and that means we keep mutating on line 11 or on line 20, etc. We never make it true. So in this case, we leverage concurrent testing.
Yeah.
Concurrent testing is more like a heavy gun, right?
Mm-hmm.
And it will solve the input packages to the package type to package 1. So which line is this? Which line? Oh, it's line 20, right?
Yeah.
Okay, so it will switch further.
Yeah. So the concurrent execution, it will get the seed 1 first, and then it solves the line 20 condition. And then now that the line 20 condition is solved, it can now switch to fuzzer, and fuzzer can explore this line 22 method, the packet handler 1. So yeah, the fuzzer will test packet handler 1, and then we find that example, maybe like there are no bugs here. So now we switch back to concurrent execution because we have to solve this line 10 in the seed 2. So seed 2 will solve the line 10 condition, and then you switch back to the fuzzer to explore this pcap handler 2, and then finally we can explore this pk handler 2 and actually we find some bugs here. So this process shows that actually it can take some time before we actually reach vulnerable code, which is pk handler 2. Yeah, so the previous 4 steps can actually take a long time, and if you time out, then actually you might not have the resources to find the vulnerable code in pk handler 2. So that's a one limitation of um, the hybrid testing, because they don't like order these seeds.
Okay, so
Yeah.
so the point is that if we take seed 2 first, so we are more likely to find pcap2 handler 2,
Yeah,
be the one. Okay.
yeah. So that's the approach for this savior that I'll explain later. Yeah, and another reason hybrid testing is inefficient is even if it manages to reach the vulnerable code, it might not be able to generate the correct inputs to reveal that vulnerability. So this is an example code. So line 12 here, basically we copy a value from this variable sec, and we copy it into section size. And then the next line that executes is line 15, where we allocate some memory based on the value of section size plus 1. So actually, an adversary can modify this section size value to be the value like 2 to the power 32 minus 1 on 32-bit systems. And then line 15, when you allocate the memory, you actually return a 0 byte due to integer overflow. So this is one example of a vulnerable code. Yeah. So so the thing is, when the fuzzer actually reaches these lines of codes, it is not probable that it manages to set a value of 2 to the power 32 minus 1 to section size, because it is
Very special.
yeah, and the inputs are randomized for fast testing, so it's a very low probability that you can actually find this vulnerability. Yeah, so those were the two reasons why it was inefficient. So now Savior, which is PD automatic vulnerability incentivized oracle. It is a bug-driven testing method, and its main objective is to cover vulnerabilities faster. So the first technique that it uses is bug-driven prioritization, which is basically prioritizing seeds with higher possibilities of vulnerabilities. So in order to do that, it collects info from the target source code to try and prioritize seeds. And it needs to predict the amount of vulnerabilities that can happen in this seed. So in order to do that, you need two things. Firstly is a method to assess what are the code regions that can be explored from an unexplored branch. Okay, so later there'll be an example. And then the second thing that you need is a metric to quantify the vulnerables, the vulnerabilities. So uses this undefined behavior sanitizer to label the potential bugs in the code.
So here, so giving your third and fourth bullets, the first is that I'm going to find the code region where the concurrent execution is applicable. Am I right?
Yeah.
So yeah, so because a lot of the code where the concurrent execution or the symbolic execution is not applicable. The last point is that it may provide maybe hard code some using the sanitizers to hard code some rules so that they can issue the vulnerability. So this slice is totally designed for seed prioritization. So next one, you will introduce how to generate a special variable value to trigger the potential bug. Because based on sanitizer, because sanitizer allows us to check the memory boundary issue, the out of memory boundary issues. So I feel that as long as we use sanitizer, I think we can fix your introduce problem as well, right? Am I right?
Yeah.
Okay, so please go on. So do you know about the symbolic execution?
I read up a bit.
A little bit. So you somehow have the idea of what is symbolic or what is concordant testing, right? Concordant execution. Okay, so in this case, I do not spend more time to explain it, because in EVA's way in the future, maybe we will use dynamic symbolic execution in the future. Okay, please go on.
Yeah. So so we give each seed an importance score. So we use it to prioritize that. So to calculate this importance score, so given a seed with n unexplored branches, okay, we have to explore each unexplored branch to figure out what code regions are reachable from these unexplored branches. And
but
from
given a seed, there's always some branch explorable and some branch covered and uncovered. How does it define an unexplorable branch?
Sorry, what's your question?
Given a seed, it always covers some branch and uncovers some branch. Right? So how does it? So does the word explore equivalent to cover?
Yeah, as in it cannot cover these branches, E1, E2, En.
Is that for relevant branches or the neighboring branch or the total branch? So consider the graph. There's a huge number of branches. So will all the uncovered branches of this seed be included, or just for the neighboring branches? So neighboring branch is here. So suppose the test goes into the going to this direction. The execution of the seed going to this direction. So definitely this one is unexplored, right?
Yeah.
There's other branch here. So suppose this is branch 1 and this is branch 2. So in your case, does only branch 1 be included, or both 1 and 2 be included here as an unexplored branch?
I'm not very sure because the example they give is quite simple.
Okay, maybe you keep going on.
Yeah, so for each of the unexplored branches, it will try and find code regions that are reachable from these branches. Then you assign UV as a L1, L2 to Ln corresponding to those branches. And then you also keep track of the number of attempts made to solve those branches from the constraint solver. And then finally, this is how you calculate the importance score. So it's a weighted average of all the labels for each branch.
So this is more like a, so does here it has the, so this is the scalar value, L1, L2 is the scalar value. It's I just know that it's a sanitizer label, right?
Yeah.
It's sanitizer labels, and this one, so each branch will corresponding to one label.
It can be, yeah, as in this L1 can correspond to a lot of labels because each branch can have multiple vulnerabilities, correct?
Each branch. So, but the why is the n is corresponded. So this is a set. L1 is a set.
Yeah.
Is a set of labels for, and this set of labels is for the branch reachable from E1 EI.
Yeah.
So let me rephrase here. So suppose this is E1, and it can reach those two. So it can reach those two labels, those two branches, and these two branch will be considered as L1.
Yeah.
Okay.
As in L1 is the vulnerability label.
Vulnerability label.
Yeah, so it is possible that L1 is empty if there are no vulnerabilities in E1.
Okay.
Yeah.
So in this case, could you please back to your examples?
Yeah. So.
Oh, you already have an example here.
Yeah.
Okay, please.
Yeah. So, the gray nodes are the nodes that are covered by the seed, but the white nodes is B5 and B7 are branches that could not be covered by the seed. So in the end, this is the.
So are B6 and B8.
B6 and B8 are branches that are covered.
B6 and B8 are branches covered. So, so what does the red lines mean? I mean the B1, 2, 3, 4. Is that as a covered branch or no? And also, I feel that given a seed, it cannot cover B6 and B8 at the same time.
Yeah, not. Yeah, the paper just says that the seed follows a path B1, B2, B3, B4. I already mentioned the B6 and B8.
Okay.
Yeah.
Mm.
Yeah, but basically they mentioned that B5 and B7 are the uncovered branches.
Branches and air. So sometimes.
Yeah. So this.
So how does the soft temps looks like? I understand it's a number of the temps to solve the branch. So in your examples, it's going to using the SMT solver to solve the B1 to solve the edges or solve the conditions from B1 to B5 and the condition from B3 to B7, right?
Yeah.
The B1 to 7. So it means that it's try a few times. We will put the label. We will put the edge from B1 to B5 into label L1 as long as we find this branch is solvable.
Yeah.
So what if we solve it for 100 times and we still cannot find a way to solve it?
I'm not sure if they mentioned that. Yeah.
Yeah, and also for L1 and L2, so what is the criteria to put a edge into L1 and L2?
What is the?
It actually is labeled by the sanitizer, right?
Yeah.
The UV sanitizer. So as long as the sanitizer finds this branch is vulnerable. So for example, it has a potential to have the out boundary error or excess access illegal memory, so it's reported. Okay. Okay. So the idea is that the harder is going to first explore um, explorable vulnerable branches.
Yeah.
Okay.
Yeah. So
Mm.
another thing to take note is if the solve attempt is very high, then the weight for that branch will be lower.
So if S is very large, it means that this branch is unexplorable.
Yeah. So the importance score will decrease.
Okay.
Yeah. So so basically this score can help to prioritize the seeds that leads to more unverified bugs, and at the same time, because of the solve attempts, as it does not get trapped with those seeds that have hard to solve branch conditions.
So here, the approach of the flooding strategy, does it adopt the SBST algorithm? So, or it just apply random, using the random seeds?
It's just using the fuzz testing.
Yeah, okay. So it largely depends on how the fuzz testing is implemented, because the fuzz testing will still using the genetic algorithm some approach, but overall the flooding does not have the idea of the branch distance. So the flooding very few flooding tool supports the branch distance. Okay, please go on.
Yeah. So that's it for the prioritization. So this is just an example of the UV sanitizer labels, and 2 points is that firstly, UV sanitizer over approximates potential vulnerabilities. So this actually ensures like soundness, because you won't miss the true bugs. Yeah, so secondly, what Savia does is bug guided verification. So what this tries to do is ensure that you can actually create inputs to satisfy the vulnerability, to trigger the vulnerability.
So that is supposed to manual effort, right?
Sorry?
So that's the part the bug guided verification. It's verified by you. Of course, we can have a run, but the result of running should be verified by human users.
As in, you can verify them through the generated inputs also.
Okay, so yeah, so as long as but when we are so this bug guided verification, so once we find a seed which can cover the corresponding branch generated by UV sanitizers, we have already verified there's a bug there. So what's special here?
The thing is, because like the sanitizer labels are over approximates like the vulnerabilities. So maybe I go through the example.
Okay.
Yeah, so basically Savia will extract the label of each vulnerability, and for each vulnerability, it will verify the predicates that are implanted in the label, and it will check according to the path condition whether this vulnerability can actually be triggered. Okay, so for example, going back to the integer overflow example, so this overflow condition, this predicate is implanted inside this label, which is section size plus 1 is more than this maximum value. So if this predicate can be satisfied, it means that this vulnerability is valid. Yeah, so what Savia does is it checks if this predicate is satisfiable under the current path condition. So it is possible that the code actually takes care of this vulnerability by checking whether section size +1 is more than this max value. So in the example that I showed, it doesn't check for this vulnerability. So actually this predicate is satisfiable under the path condition. Yeah. So if it is satisfiable, then it will generate this input and trigger the vulnerability through the test case.
Okay.
Yeah.
So this is fairly straightforward.
Mm.
And this is overall structure.
Yeah. So this is the overall architecture of Savior. You can just focus on this red portion. So the first step is the fuzzer. It will just randomize inputs and generate seeds. And then we have this coordinator component, okay, that will it basically the bridge between the fuzzer and the concordant executor. So when the fuzzer generates the initial seeds, the coordinator will prioritize them based on the number of labels. Yeah, so at this first step, actually Si will be 0 lah, because it hasn't done any constraint solving yet. So all the seeds are just prioritized based on the number of labels. So for seeds that have high number of labels, which means high possibilities of vulnerabilities, then the concurrent executor will try to solve those path conditions, those conditions first. And so the second step, the concurrent executor will actually pass the test cases to the coordinator, and then the coordinator can then prioritize the seeds based on the number of attempts that the concurrent executor made to solve the uncovered ranges. And then, so at this second step, the SI will be, there will be some input in SI, and then we prioritize this. So then we pass the seeds back to the fuzzer, and then the fuzzer can then explore the unexplored code regions. Yeah. Then
the fundamental idea is that I think the major contribution. I think this paper, of course, Aaron, you made an excellent job to present this paper. I feel all the stuff is very clear, and also understand you. I also now, based on your explanation, I also understand you under this paper quite well. But from the research point of view, I think for this paper, the major contribution is that it's going to try to let the further forget about those branches, which is very hard to be solved by constraint solving.
Yeah.
The major idea is going to solve. As for the synthesizer, I think there's a lot of as long as we can, because combining AFL and synthesizers is a very traditional way to do this. So it is going to generate. So the idea of the synthesizers is actually generate a set of assertions in the programs, and it's going to guide the FL to generate seed reaching those assertions, reaching to the true branch of this assertion. As long as these assertions has been satisfied, it means that we found a bug, right?
Yeah.
It means that we can find a bug. So this approach, this is very general approach. So, and this part is more like a target oriented fuzzing. It's also very much like what we do in our applied on EVA suite. Despite we are not working on AFL, but we work on EVA suite. The idea is very similar. I think for this paper, all it's done is that because when we do the fuzzing, the time is very efficient. The time is very important. You can see, suppose we have a budget of 100 times. If all the time is used for initialization, or if all the time is used for constraint solving, then we have very little time to do the real fuzzing. So in this case, all the contribution of this paper, based on your presentation, seems to be to using an equation to forget about the branch, which is very hard to solve. So for example, if we solve for we have a lot of attempts to solve a branch, but we find that it has out of the reach of constraint solving. So we never touch this branch because there are so many branches there, and there are so many generated branches by sanitizer. So why bother to put those hard solving constraints? We can just to pick the lower hanging fruit. Yeah, I think that's the basic idea of this. Okay, please go on.
So that's about it for the approach. Just go through the evaluation. So the first technique that Xavier does is a bug-driven prioritization. So whether we can find vulnerabilities quicker. So the first graph on the left is basically the number of bugs that we reach. So it's most of the different hybrid testing approaches, it reaches the same number of bugs.
It's no difference. There's no difference.
Yeah.
Is this paper accepted? So it does not find new vulnerability there.
So the thing is, it actually reaches the bugs, but it doesn't actually trigger the bugs from the second graph.
So from this graph, we can only see that it does not. It only speed up. It only speed up the bug discovery process, but it does not explore more branches. So the idea, so that's still reasonable. That as long as we let the further run sufficient long time, and all the bug found by Xavier can be found by those traditional approach. Right?
Yeah, but not all the bugs that are reached are triggered. Like, as if on the
not
right
all
graph.
the bugs are triggered. What do you mean?
So like the trigger means that they are able to find the inputs that actually.
Is there the disconnection? Will you please again?
Trigger means like they can actually get the inputs that cause the bugs to fail. So like for example, the integer overflow actually manages to find the input to cause the overflow.
So that means the Xavier or that is a bug. Oh, okay, I see. So that is reach the lava. Okay, so it means that they reached the bug, but they did not trigger it. So does the baseline adopt sanitizer? Okay, so I think the problem is that those approaches are designed for coverage, so there's no need for them to be combined with the sanitizer, right? So it's very likely they did not combine with sanitizer. Okay.
Then the next one is the verification. So they just want to see if they can find more vulnerabilities. So so left table is the number of bugs that are triggered before they do this verification method, and then the right table is when they actually use the bug-driven verification method. Yeah, so they applied it to different others, and
these two tables are similar. No, not similar. So that means the one hybrid. that means using their own vulnerability discovering approach, they can largely improve AFL goal. Right?
Yeah.
And then the rest tools may helpfully combined with the sanitizer. So yeah, so basically they are using a sanitizer to verify it.
Yeah, so yeah, that's basically it for the evaluation. Yeah, so Savior is a testing method that is bug driven instead of coverage driven, and then it uses these two techniques, and so yeah, it tries to run seeds with more vulnerable potential, and yeah, based on the results, it's able to actually find more vulnerability than the current existing methods.
Yeah. So overall, I think I may have some comments here. So there's a huge difference between the software engineering conference and the security conference. So usually the security conference does not emphasize on a very sound technique. So suppose there's a few okay or fine technique that is security would be appreciated. Nevertheless, security conference highly emphasize on the result. So for example, given approach, frankly, I feel this funding approach does not have very strong novelty. Nevertheless, it still have very impressive, impressive result that showing that they have discovered more bugs in existing programs. So, so in this case, we may think about it. So this paper can hardly accepted in software engineering conference, but for us, we have developed some object construction graph. So overall, I think our approach is more novel than this work. But if we only work on the coverage, this work will never accepted in security conference, because if we really want to show the strength of our work, we need to apply our tool on the real world systems and find some real world bug. So that's the ultimate. That's what can be accepted in the security conference. Okay. So Aaron did a very good job, and both Aaron and Ruofan did a very good job on presenting the papers, and both presentations are really clear. And for the Aaron's presentation, maybe there's less students work with Aaron, but I think Aaron has reached a very good, it gradually gained its own expertise based on the paper reading, and again from the working on the testing tool. And yeah, I feel that I still feel quite optimistic of your future research. And I also know that a lot of you, maybe let me stop recording the video.